We continue. And so this optimization problem, as we remember, might have constraints, and they are crucial for the success in practice of MPC. So I summarize them by these little functions h that could be reflecting bounds on the controls or on the states. And we typically have these terminal constraint Sn, which will play a very important role in the stability theory. Is everything okay, Katrin?
Now it works.
Now it works? Yeah, okay. So this is the optimization problem statement, and I follow the suggestion that was made yesterday that we could actually just regard S as a parameter here because it makes it notationally easy in this context. So we will not have S as an optimization variable. So we start our optimization with state S1, A1, S2, A2, up to Sn, right? So let's maybe put it here. You remember all the variables. I left out A0, about which we also optimize, of course. I just separated for a mini notational trick, because I'm actually interested. I mean, if I solve this problem with a min for over all variables and the S0 is fixed, then this is actually entering this problem. So this is a parametric problem in the variable S0, which is actually my parameter that enters. But I'm only interested in this output, so I put that separate. That's why I put it here. And now the feedback law that I get with MPC. I need a bit more space, sorry. Good, so I have here this. This needs more space here. S1, A1, up to Sn. Here we have the min over the A0, and then we have the arg, because that's the only argument we are interested in, and this is like my notational trick for that. This is a function of S0, and I also put an index for the n, which is the time horizon. So I'm interested in getting the feedback that is basically the optimal action for A0. Yeah? So let me put this into a big box. That's defining our MPC feedback. And to clarify it even more, to just be sure that we are completely on one page, this MPC feedback for horizon length n for a given S0 is of course identical to the A0 star, where A0 star is the first control of the solution of that problem. Yeah? Sometimes we will actually omit these constraints and just use these extended value extensions that might then I put a bar on top. But for the moment we don't need that, and we really want to solve this as an NLP online, yeah? And then apply this feedback, and that's what MPC does. It has this property that it's looking only n steps into the future, so it's really a concern what happens after these n steps, right? And in fact, even after one time step, we already move our horizon forward, and so it's absolutely not clear what happens with a closed loop system. So what is now the closed loop system? That's a definition that we should be aware of, the definition of the MPC closed loop. MPC closed loop system. And this system is given by the system dynamics, which is just Si plus 1 equals f of Si. And then as a control, we plug in the feedback law that we get from MPC, which is this function here, right? Pi MPC horizon length n of Si. And so in this notation, I already assume that I have at time point I perfectly and instantly available the solution of this optimization problem. This is a bit of an abstraction, you see, right? How could we have it available at no time? But this is the assumption we make here. And I will actually give this a shorthand because I don't want to write this pi of MPC all the time, right? So we give it a shorthand and we just say FCL of Si. Yeah, so that's also expressing very clearly the fact that our closed loop system is a system without controls, yeah, because now the controls are inside the system. So let me just visualize that in a graph briefly what we do. Right, so we have our system. That's the system without our controller. Yeah? It has actions that we put into it, and it has states that we can measure. And then we have our MPC controller, and that actually sends these states back to our system. Yeah? Of course, I could also make this little visualization, right? So that's like I plus 1. There's a little bit of a delay somewhere in the system. And that's, so to say, expressing the fact that we have memory. But it's basically this equation. Yeah? So we look at this whole thing as one system. And this whole system is the closed loop system. And that's governed by this dynamics f of closed loop CL of SI. So we can actually forget about the A's. They are just, so to say, an internal quantity of our system, which we are not really interested in the stability analysis, right? So for stability analysis, we need to look only at this system. And so the question is, what does it mean that a system is stable or not? Yeah, so let us just think what we intuitively want. Intuitively, we want, if you think of this whole thing being in state space, so this could be one component, say S1, it could be a second component of the state. So when you start somewhere, you would like to move somehow to a steady state. That's the desired one, and we use typically the origin because it makes all our notation a bit easier. Yeah? So stability of the origin is our aim. S equals 0 is the aim. That's the whole aim of this lecture, nothing more. Just we want to show that our system goes to 0 if we do design our MPC controller suitably. And that's not completely easy, but it's also not impossible. So let us first define what stability really means in a system theoretic setting. Maybe I should also say in all this graph already, yeah, we are now talking about continuous state spaces. Yeah? So otherwise the following definitions don't really make sense. So let me give you a definition of stability of any system. And so basically, if you think of it, I do the same plot here. I have my origin. I have, as I said, two components of my state. Then what I somehow want is that if I'm not, I mean, local stability is the following. If I'm, if I go close enough to the origin, then I stay in the neighborhood of the origin. That's basically what local stability means. So let me just define it. System. So let me just say Si plus 1 equals F CL Si. I keep using the CL here. That's not too clumsy, but it holds for any other system as well, right? Is locally stable, okay, at the origin, of course. That's our restriction here without any loss of generality. And the definition for this is that you want to be able to stay in a neighborhood. And you express it the following. I first do the mathematical expression. So you say for every epsilon, so every neighborhood in which you want to stay, you can find an delta, it's also possibly bigger than 0, so that your trajectories, if you start with a state that's smaller than delta, then this implies that all states are smaller than epsilon for I from 0 up to infinity, right? So you see already that the delta can be bigger than epsilon, but not smaller, otherwise it wouldn't cover the first state. But the main point is, so if you, sorry, the delta can be smaller, right, but not bigger. So for all, I should say for all S0, so that the S0 is smaller than delta, then the whole trajectory remains in the inside the epsilon environment. So basically, someone would say, I want to be in this epsilon ball, and this is arbitrary. It could be arbitrarily small. So someone tells me, can you find a delta so that you stay in this epsilon ball? And then if I can then give this person a delta ball around the origin, so that when I start in this delta ball, then I might maybe go out a bit, but then I stay in this epsilon environment. So that is already a stable system now, if you can find that, but for every epsilon. And that means if someone gives me a very small epsilon, I will also stay in this very small neighborhood. Yeah? Obviously, this isn't exactly what I want, right? So I usually want that I also get attracted by the origin. Yeah? So this is just stable. Yeah? Locally stable is this, right? But how do I actually express my other desire? And that is asymptotic stability. Let's use the right word. Let's just make it even stronger. I use the word globally attractive. So I want my system to be globally attractive as well, and this origin should be steady. Should be a steady state. And if globally attractive just means independent where I start, S0 element in the whole state space, right? That implies that I have all the SIs, the sequence of SIs, maybe converges to 0 as I goes to infinity. Yeah, this is now a property for every single trajectory, and I use now this SI. Whenever I use SI, I mean a trajectory that follows the closed loop dynamics, right? So that's implicit here. It's basically, you could also make a more clumsy notation than the S, if as we did with single shooting, would be basically, so I could also say SI is here identical to what we called before SI tilde, and then it would just depend on S0, right? So on every S0 you generate a full trajectory. You could define that really as a function by the simulation, but this is just a side remark. I think it's clear from this context that we mean a trajectory, right? So locally stable means however small you choose your neighborhood, you can find a possibly bigger neighborhood so that you remain in that. And a possibly smaller neighborhood so that you remain in the epsilon ball. But the epsilon ball can be arbitrarily small, and that's what makes it an interesting definition. That's actually due to Lyapunov. And it's a bit like continuity of functions, but that's stability for continuous systems. This is in discrete time. You can also have it in continuous time. It's nearly the same. So these are, I think, the definitions I wanted to make. But I want to directly tell you already that there is a tool that people use a lot in systems theory to control, to prove stability, and that is also due to Lyapunov. Yeah? So the same person who defined that, what we just wrote down, and he invented the concept of a Lyapunov function. And a Lyapunov function is an extremely powerful tool, in particular for MPC. Yeah? So definition, what is a Lyapunov function? Yeah? Lyapunov function for a system that we call Si plus 1 equals FCL Si at the origin also. Yeah? So it can be defined with respect to other points if you like, but it's a Lyapunov function at the origin. And what is it? So first, V is a function from the state space to the real numbers. Yeah. Is a Lyapunov function if and only if the following holds. So first of all, this V should be a positive function. And I think this is maybe trivial, but let me just say it's even more than this. It's actually a positive function which has a lower bound, call it alpha 1 of S. I specify that a bit later. This is a lower bound for our function, V of S, and it has an upper bound as well that we call alpha 2 of S. And alpha 1 and alpha 2 are what we call K infinity functions. And that means that alpha, and actually I put norm here. So they depend only on the norm. So they are scalar functions. So they are functions that go from R plus to R plus actually. And basically what they do is they are monotonously decreasing. So alpha I at 0 is 0. And then alpha I of some value that I maybe call, well, how do I call it? T, just some variable here. T1 is bigger than alpha I of T2 if T1 is bigger than T2, so it's monotonously increasing, right? And it's also going to infinity, so alpha T goes to infinity if T goes to infinity. So the picture for this function I think we should have in mind is if this is T and that's alpha, then it's a function that just goes up. Yeah. What is nice about the Lyapunov function is that it's, this upper bound means you're just having something that's penalizing when you go away from 0, so to say. It has a lower and an upper bound. That just means that this V has a decent property in terms of being a kind of norm. It's not a norm, but it's a generalized form of norm. Yeah? Actually, there exist other definitions where it doesn't go to infinity. So this is, sorry, I think I take it for the whole state space here. So I make it general. Yeah? So that's but making. Each time step alpha decreases. No, sorry. This is not about time steps. This is in state space. Mm-hmm. And alpha is, this is not time. This is not time. Sorry, I should not have called it time. It's T. It's just a variable. Maybe I call it Z or something. Yeah, let me call it Z, so not to make any confusion. It's good that you mentioned, so it's Z, something else. It's just a scalar variable. It's actually the norm of our state. Yeah. So it's just a penalty that shows that, the picture that you should have here, if this is state space, S1, S2, then you have some, the Lyapunov function is a function. By this definition, because alpha at 0, it must be 0, right? This also must be 0, and it should be bigger than 0, but then basically this implies already that our Lyapunov function at 0 is 0, right? And then the positive, the fact that it's increasing means that 0 is the only point where it's 0, right? So there could be other points, and if I visualize my Lyapunov function, it could have level lines that look maybe like this, right? Somehow it could be not shaped like a norm. It's a non-convex function possibly, but it has these upper and lower bounds which make sure that it's actually nicely behaving and penalizing distances from 0 in some form. Yeah? So all these level sets are actually later on also very important in all these stability proofs. Yeah? And so this is like the first condition that we need, and the second one, and that is that there. First of all, I should say there exists, right? So it's equivalent to the existence of functions alpha 1, alpha 2, and alpha 3. Yeah? And alpha 3 now is a function that tells us how much we decrease in every time step. And what we want actually is that if you start somewhere, that is Si, then you will go somewhere to another point Si plus 1. Which is, of course, the closed loop system started as Si, right? And what we want to, so to say, also assume, and that's actually part of the definition of a Lyapunov function, is that this Lyapunov function value at the new state is smaller, and strictly smaller, than the starting point. So what we want is that V of F, closed loop, of any S, right, is smaller than the V of S minus a function alpha 3, which again could depend somehow on S, could be on the norm of S or S itself. And this function, let me just define it alpha 3 is, I forgot continuity for this. All functions should be continuous here. And alpha 3 is continuous and positive definite. You might say, hey, we have heard about positive definite matrices. I know what that is, but how can a function be positive definite, right? It can be, and the definition of it is basically what the word means. Positive definite means it's only zero if the input is zero. So it is actually just a function so that alpha 3 at 0 is 0, and alpha 3, if you're not at 0, you're bigger than 0. S is not 0. That's it. So simple. Yeah? So it's just a continuous function which is 0 at the origin and non-zero everywhere else. So if you want to visualize this alpha 3, so this is like alpha 1 and alpha 2. And now if you visualize alpha 3, I can define it in the full state space. It could be any function like this, right? So it's not even needing to be monotonously increasing or something. That's it. Yeah? 0 at 0 and positive everywhere else. There's a question. Where was it? Yes?
Yeah, usually I always see the definition of a Lyapunov function with
three functions?
Yeah, exactly. So v of 0 is 0.
Yeah.
And v of x is larger than 0 if x is not 0.
Yeah.
Is there any benefit of defining it with the...
With the upper and lower bounds? Yeah, I find it more compact.
More compact?
Yes, yeah. So, you have... let's just stick to that. There are many different definitions of them, and also it depends if you have the full space or not the full space. So that could be k infinity. Sometimes it's not k infinity. I just took the definition that Jim likes most because I follow his way of reasoning. Then we can build on his theorems, so to say. Yeah? But I should say that there are many possible different definitions. Okay, so but the intuition is this one. Have this picture in mind, right? So it's a positive. Also, the Lyapunov function, by the way, is positive definite, right? By this very definition, but it's more than positive definite. It has this property that it has an upper and a lower bound of a function that's monotonously increasing. And so if you think of z being the distance, so to say, then here could be the upper bound. So that would be alpha 2, right? This would be alpha 1. And then if you take, so to say, of course this is not exactly defined because that is just the radius, right? While S is the full state space. Yeah? But you could think of your Lyapunov function V to be something in between here. Yeah? So that's V. So it has an upper and a lower bound. And in that sense, it must be positive definite, but it's even more because it has this lower bound here. Okay, and then it has this beautiful second thing that if you're not at 0, and now that's interesting. So what happens at 0? This function is 0, right? This function is also 0 at 0. So at 0, the Lyapunov function will obviously stay 0. Now that's implicit in this definition. So in this definition, you see already that f closed loop of 0 is 0, right? So there cannot be a Lyapunov function if the system isn't stable, if 0 isn't a fixed point. But now the interesting thing is, so that's already one implication of this definition that it must be a fixed point. But in fact, the whole fact is, and that's now the beauty of everything, and that's a theorem that's also due to Lyapunov, and that's why he invented these Lyapunov functions. If there exists a Lyapunov function V for our system, yeah, at the origin and so on. So exactly following this definition, maybe I draw a box around it. If you have such a Lyapunov function, then, and now I think we can get both things together. Yeah? Okay, if it's, this would be for the whole space, but then the origin is stable and attractive. even stronger properties you could deduce, but these main properties, it's a stable, or the origin is now a stable point, and every trajectory will go to that point. So that's what we want, right? And the proof is relatively intuitive, but let's not do it in math here, but you see it already from this picture. You are somewhere, you know that your Lyapunov function will decrease because of this property, yeah? When you do one step. And so if it decreases, then obviously also the value of v will decrease. Yeah? And that means when it can only decrease, it means that if you're once in a level set, this first condition basically just determines that your level sets are somehow a form of distance around the origin. That's what they ensure. They are just measuring in some strange norm, it's not a norm, in some strange, with a function, with a Lyapunov function, you measure distances from zero. And they have the property that each level set is contained in the other. So it's really a sequence, a shrinking sequence of level sets. And if you are in one level set, you will never ever exit that level set again, because you can only decrease. Yeah? Even more, if you're not at zero, then you will, from one level set, always go into a level set which is a bit smaller. So in that sense, you do not only leave a level set, you never leave the level set, that's what makes it stable, right? But you also reduce the level sets all the time, and that's why you can actually, you will converge. Only if you're at zero, you stay there, and then your function isn't decreasing anymore. So once you have found a Lyapunov function, you have shown stability, and that's why people in stability theory really like to construct Lyapunov functions, because then afterwards no one asks a question anymore. Yeah? So if you find a Lyapunov function for your system, you will be happy. And so now the question is, can we find Lyapunov functions for MPC? Yeah? Maybe before we go on, because we have this convenient setup with a recording, I would invite possibly one or two questions if there are some things that need clarification.
So there's a question from the chat. What happens if the origin is not stable and attractive?
What happens if this origin is not stable and attractive? That's a very good point. So let's just say, this theorem says if there exists a Lyapunov function, then the origin is stable and attractive, right? So conversely, when you say when the origin isn't stable and attractive, right, then there exists no Lyapunov function. That's as simple as that. So then it doesn't mean that, the problem is the following. If you do not find a Lyapunov function, you don't know anything. Yeah? But if you have found a Lyapunov function, then you know it's stable and attractive. So that's like a beautiful tool to show that you are stable, right? The other thing is, if you somehow with one single trajectory, you can show that your origin isn't attractive, for example, right? You prove that you're going away or you're never approaching zero. If you have found such a single trajectory, then you have already disproven the existence of a Lyapunov function. Yeah? So this is an interesting relation, right? So Lyapunov functions are a sufficient condition for stability. And under some circumstances, surely also necessary, but I'm not deep enough in this, and there would be certainly some technical conditions, yeah? But they are the main tool for proving stability. There's a second question.
Maybe I have a question.
Yes?
The lower bound function, why do we need it? Can you explain it again? So probably does not have zero values?
Yeah, this lower bound is, in some sense, it's a slightly stronger statement than saying that V is positive definite. Yeah. So if you have just and as I said, you can have these more traditional. You just say V is positive definite and it has an upper bound. That could also be fine. Yeah. But with this, you somehow, you have really nicely shaped level sets.
Now there are two more questions in the chat, 3. Okay, the first one is is condition A the same to that the function V is positive definite and radially unbounded? I think
it's very related. Sorry, I didn't go into all these. So the question I have to repeat, is it the same as that it's positive definite and radially unbounded? It's very similar, at least. I cannot say if it's exactly equivalent.
is the Lyapunov function monotonic?
No, the question is if is the Lyapunov function monotonic, and it is not. Please keep in mind the Lyapunov function is a function of the whole state space. We should always imagine it here at least in 2 dimensions to get the idea. It's not monotonic because the state space, I mean, you can go in any direction away. It's just growing. But maybe I should draw another level set just for the fun of it. There could be also, this could be the next level set. Yeah, just for fun. This could be another level set, right? And so if you would even go in one direction, let's say on this axis, yeah, it's not even monotonic in that direction. Yeah? So that's why you only have these bounds. The bounds can be loose and so on, but you want to have it actually general as this. Yeah? So the upper bound can be significantly higher than the lower bound, and then you can accommodate even such functions. Yeah, so the V, as I plotted here, so it could be, this would be possible.
Okay, so there's one last question.
Yeah.
Maybe we also answered later. What impact will a non-stable, non-attractive origin have on predictive control?
Okay, so the question is, what impact does an unstable, non-attractive origin have on MPC? And this is actually, let's say, a little bit of a misnomer, right? Because a system can only be stable or unstable under closed loop. Because if the action is unspecified, the system is also unspecified, right? If I, so to say, I cannot talk about stability of the system before I define what controller it has. So if you say what implication does an unstable system have on MPC, then I try to interpret the question the following. So imagine that you have this trivial controller where you put all A's to 0. That would be like one option. Yeah? It's like you might think of doing nothing. That's, of course, if you do nothing, you haven't taken a decision to do nothing. That's a decision, right? But anyway, so let's assume that, for example, linear systems, this might be very well defined. So then you can define that the system with no action or with 0 action is unstable or unstable. And now an MPC controller, like any other controller, can actually stabilize. If the system has controllability properties, it can stabilize an open loop unstable system. Yeah? So in that sense, MPC and other control techniques can deal with systems that would be unstable if you don't control them, so to say. But in this language, it's a bit difficult to talk about them because I need to specify what I have. What feedback law? Thank you. I think the questions helped already to get me into touch with all the things that are in your mind. And I think it's really then time to go to the stability of MPC. And that's, of course, what we want to prove. So let me say what is the main idea here. The main idea is we have an optimization problem. We have some degrees of freedom of how to choose things in this problem, namely the cost function, maybe the constraints. Yeah? And so now we choose a cost function C that is somehow positive definite. That will allow us, so to say, to later we will see that this will allow us to, so to say, have a shrinking Lyapunov function. So there are basically 2 ideas. The one is that you just penalize deviations from 0, so to say, right, with your cost function. And the second is that you add extra things so that the optimal cost of this is a Lyapunov function. Yeah? So maybe let me say what the idea is. Use the optimal cost to go as Lyapunov function. That's the idea. And so let's but after, yeah, use positive definite stage cost. That's one of the other ideas. C as Q as A. Yeah. we come back to that in a minute, and add extra penalties and constraints. Constraints, penalties, at end of horizon. Basically on SN, this last state. Yeah? Yes?
So is this a recipe how to, if we start with an MPC, then we use these ideas to find an MPC that is stable? Or is this like, here is an MPC, and because that's...
Yeah, no, exactly.
The answer, right? Here is an MPC,
yeah.
is an MPC, is it stable or not?
Yeah, so the question was, is this a recipe of how to construct the MPC, or is it a recipe of how to prove that an MPC is stable? In fact, it's both in one, right? So basically, before you design your controller, I could try to separate them, and maybe that's what I should do, yeah? So maybe I first talk about this. This is a recipe which would be a sufficient condition for stability, yeah? And afterwards, I'd use the two others in order to make it true, right? So the first idea is actually the following, and let me just, maybe I order them. So I just say this is like 1, 2, and 3. And so let's specify now on each of them. And 1 is actually the crucial recipe, the crucial tool for the proving. And then the others are then recipes of making that possible. So the assumption here, which is like a typical assumption in control engineering, is the system model is given. I mean, you don't want to invent your model, right? That's not what we want to do in control engineering. We assume that we have identified, modeled nicely. Now we know what the system is. But what we are allowed to do is we are allowed to say what penalty we impose on deviations and so on. So that's a design parameter, and that's why we are allowed to change these two things. So in the optimization problem statement, we would be not allowed to change F for sure, but all the rest is open to discussion, and that's why I added these here. But thank you for pointing out this question. So the idea is actually to just take SV of S0, I call it, right? The minimizing function of this problem. Min of A0, A1 up to n minus 1, S1 up to Sn of the cost C Si Ai plus E Sn. And then maybe I put here already the bar. You remember what the bar means? Just means that I don't have to talk about the constraints anymore. At least not the inequalities, and now I add my Si plus 1 equals Sf of Si Ai. It's just making my notation a bit easier here. So it means also that this function would be infinity when we are not feasible, when I cannot solve the problem. Okay, so maybe I do it a bit mixed, but just to I put the R, this away, and I add at least my terminal constraint because yeah, exactly. I want to talk about that separately later. Yeah, so this is now again in the constraints. Okay, so this is like, by the way, this is something that we defined before, and I think I called it J0 in the previous talk, right? Yeah, so that is J0, it's nothing else. In the dynamic programming talk, we called it J0. It's the same as this. And maybe now, because I have this MPC control law, right, so I should give it maybe MPC and an index k, n for the horizon length, right? Because that could be useful later. So this is the value function, and now the question is this a Lyapunov function or not? But the idea is to take that as a Lyapunov function. I think in order to continue, I need to clean the upper blackboard. So we make a mini break and take a picture, and then I clean the upper blackboard, and then I move this one to the top.
Function for controller, and then she was using it as optional.
Exactly, yes. Yes, so you can.
So choose first finding it, proving that it's stable, and then using the same as cost function.
We should discuss later. So the question is if you could first define a Lyapunov function and then afterwards use that in order to define your optimization problem. It's a bit difficult actually to find a Lyapunov function, but actually you're right also. And that's very true actually that most MPC stability is actually based on some terminal function which is already a kind of Lyapunov function but in a smaller region. But I come back to that maybe when we construct it really explicitly. Then I give you already my preferred way to construct it. Maybe I tell you already because it's easy and I mean usually this function is, when you have an optimization problem, you can define it, so to say, and then after, with some conditions, you can make it a Lyapunov function. A lot of the literature starts already by saying the end weight should be a Lyapunov function. But this is sometimes difficult to construct, and what you can always construct is, you could say if I'm at the origin, and my system has this property that if I'm at 0, I stay at 0, then at least the origin is, so to say, positive invariant as a set. And so what we will later do is actually we will impose by constraints that we should end our trajectory in the origin, and then we don't have to think about this function here anymore. And that I think is the cleanest, or the easiest, at least the easiest way to create a stable Lyapunov function for MPC, and that's what I will do, let's say, as one example later. Yes, please?
So there is another question. Could you give a simple example of a system that does not satisfy the Lyapunov theorem?
Yeah, so I should give a simple example of a system that doesn't satisfy Lyapunov theory. Okay, actually, I would give a system and a steady state that is unstable. And then I'm sure that no one will be ever able to find a Lyapunov function for this unstable system. So let me do that once I have cleaned the blackboard. Did you photograph both blackboards already? Wonderful. I move the one up, which I will not change anymore, and then the other down. And then I give a simple example of a system where actually we cannot find a Lyapunov function. Okay, but first I clean the blackboard. And this system you can maybe already start thinking yourself. What could it be? An unstable system. Any unstable system would be okay. Yeah, take your maybe a half a minute break if you like to pick up a coffee. Okay, maybe this example is just for unstable system. That's actually it, right? Without Lyapunov function. And this is just, for example, Si plus 1 is equal to 2 times Si. Yeah. So here I have the origin is stable. So 0 is equal to FCL of 0, right? Sorry, it's not stable, it's a fixed point. Yeah? But I will never stay in this fixed point, and you can, if it doesn't have a Lyapunov function because it's unstable. There might be some systems which are stable and don't have a Lyapunov function, but I don't know examples for that. Yeah.
If you start from 0, how would you get out of 0? Each next state can stay at 0.
You're absolutely right. So the point is, if you start in 0, you would never go out of 0. That's true. Yes, exactly. But it's not stable. It's an unstable fixed point. It's a fixed point, but it's not a stable fixed point. And that's exactly the key to stability in system theory, right? So we don't have the inverted pendulum, but that's like the prime example of an unstable Yeah, we have a wonderful example. Great. It's so big that we can have it's unstable, but with a decent time scale that is slow enough for our camera to work. So here I have an example for a system for which I cannot find a Lyapunov function, at least not for this steady state. I hold it, maybe I hold it here at my belly, just to make, maybe I hold it with this hand, and then I don't control it. See? Even though it started in 0, it didn't stay there because it's unstable. Obviously, mathematically, I might be able to really put it into 0, but then you have always these little real-world disturbances. And so even if I try really hard, then maybe I would, if I'm really good, then maybe it would stay for 2 minutes. I don't think it's possible, but maybe for some time longer than what you see here, but at some point it will fall down. Huh? And if I now apply a controller to that, I measure the angle and then I'm able to move this, then obviously I'm able to stabilize it. And so if you now want to construct a Lyapunov function for me and the stick together, yeah, you could do that maybe because we can balance it. But I can only do so because I have feedback. Yeah? If I don't watch, now I watch the camera. Impossible. I have to watch there, right? So if the feedback is broken, that's not possible anymore. Okay, so that's a simple example for stable and unstable systems. So yeah. Thank you for the question. It's always good to have basic questions. So fixed points can be stable or unstable. This is an unstable fixed point. Okay, but coming back to the idea, so we have our idea so that this should be a Lyapunov function. But how can we make it a Lyapunov function? And now come the ingredients. What we want to show, so to say, and the crucial thing is actually that it should be positive definite, right, as a function. So how can we prove A and B? And the most difficult part will be actually B. So we need to make sure that it's decreasing. So let me just say that for the two other points, so we use now positive definite stage cost. So we just impose, so that's an assumption, and this is already a design question. Yeah. So now we are designing, so we assume that C of S and A is something that's, let me just make it correct. It's something that is exactly bigger or equal than some nice function that we maybe call alpha 4, right? It's something like this of S, where alpha 4 is positive definite. So we make it actually 0, and then also we have C of 0, and 0 is equal to 0. So that's another thing we assume. And something that we have to assume always, and that's unfortunately not an assumption on our cost, but it's an assumption on our system, we should assume that we have a steady state at 0. 0 control and 0 state keep you at 0. I mean, that doesn't mean it must be a fixed point that is stable, it just means it must be a fixed point. Yeah? So we want to have a fixed point. This is a system assumption, but we also need to impose it. Yeah? So we can stay in the origin and we can stay there at 0 cost. That's the two things. So that's a beautiful thing. Now, if you're in 0, you stay in 0 and you remain there. That means already all these assumptions they will imply. What do they imply? That your Lyapunov function, MPC, if you impose the problem at 0, yeah, if you solve that optimization problem at 0 cost, yeah, and of course your constraints are feasible. I should say that you also assume that E of S of 0 is 0, right? And that R of 0 is smaller than 0, right? That's what you also assume. Yeah? Maybe not be too restrictive. Yeah? So somehow this is what you assume. So 0 must be a feasible trajectory. And that means, because it's positive everywhere, right? And it is 0 at 0, then there is a solution to that problem where you just stay at 0 all the time, and that solution has the cost 0. So you know V0 is 0. So that is by these assumptions you can easily show that. And you also have shown, because it's positive definite, that it's V of MPC n of S is bigger than 0 if S is not equal to 0. Why is it bigger than 0? Could it also be 0? No. Why is it bigger than 0? The reason is that already your first stage cost, you start counting at 0. This first stage cost already contains one of these terms, and so that's definitely bigger than alpha 4 of S0, right? So that sense, maybe I don't write it, but that's all the implications here. So I have already positive definiteness. With a little bit more, I can somehow get the assumption A done. Yeah, so I will omit details, and I can just say this all will imply A. So the first condition of Lyapunov. Yeah? I should also say that this should be positive definite, so it shouldn't be coming negative and so on. Obviously, you don't want to have a possibility that you can go. So yeah, I forgot that, right? So it's always positive, this E. So there is no way to get a better cost than 0. So let's say these are more the technical conditions. I mean, I have a positive definite function, and with a little bit more details, I get the alpha 1 and the alpha 2. But now I want to get the B condition. So how do I get B? Huh? How can I show that I'm always decreasing my cost? And that will be a bit more difficult here. And I can just tell you what I would need for that. And for this, so now the question is how to prove B. How to prove B. And here I need to add extra conditions. So maybe first I give the intuition. So I have my time horizon to time n. I start at time 0. I have my starting state S, which isn't 0. Yeah? And then I have my trajectory somehow that I plan. And I want to go close to 0, so maybe I'm getting close to 0, hopefully, because I penalize being away, right? So that could be my solution here. It could also look differently. That's roughly the intuition. What I do now is I move forward my system by one time step. I apply this control A0, and now I assume that my system is identical to the system that I have in my prediction. Yeah? That's also a crucial assumption that I didn't make explicit, but that's throughout this talk. We talk about system in MPC and system in reality are equal, which is a very strong assumption in reality, right? But that's what we call nominal system. So the system, but this is the one for which we want to first design a controller. So then we will be here at the state that we could call S1, right? And at this state, we have to evaluate our Lyapunov function again. So what is this Lyapunov function there? I mean, here we start the problem. Now we will have a horizon that's a bit longer. And for this horizon, now we can optimize the whole thing again. And we want that this whole thing is then, that this is strictly smaller than the Lyapunov function at V0. So what we want is that this is somehow smaller. Yeah? So let me just say what it in words, so to say. What we want is that Vn MPC of S1 is smaller or equal to Vn MPC of S0 minus some function alpha 3 of S0, right? That's what we need to show. And that's not so easy because, I mean, this function, intuitively you would say, okay, somehow, why would it go smaller? What could be a reason why it's smaller? Maybe the reason could be that here I have to, somehow I will add something, right? So that's nasty, I add something. I want it to become small, but here I have to add something, right? Because the horizon gets moved forward. Here I might lose something because I'm making something moving out of my horizon. And now the trick is, so to say, that we want to show, we want to use actually our stage cost as this alpha 3 function over there. Yeah? So what we will, and the stage cost satisfies this with this alpha 4 function. So the idea is the following. We will be able to show that V MPC n of S1 should be smaller than Vn MPC of S0 minus C of S0. And of course, here we need to have the MPC feedback, right? MPC n of S0. So that's what we want to show. And that's also not trivial to show, but that's our idea. Yeah? So the idea is if you take this cost and you add to it this part of the cost, then you get basically the horizon for n plus 1, so to say. Yeah? But it's not that easy. But there is one thing, and here we use the principle of optimality. What we can immediately show is the following, namely that if we would just shrink our horizon, yeah, then by the principle of optimality, let me just say what we know already. We know actually that this function v n minus 1 of MPC at S1 is equal to Vn MPC of S0 minus C of S0, and here we have this feedback law, right? MPC n of S0, which is actually the control that we use in our closed loop controller, right? So this one we know. Because, I mean, now please look at this little notation detail, right? N minus 1, I added here this index in order to express the horizon length. And so the optimal solution for the problem that starts at this state but ends already here. This has only a length of n minus 1 from here on, right? So that's what I know from the principle of optimality, that it must, by definition, if this was optimal, then the subarc must be optimal as well. That's what by the principle of optimality. So in that sense, we are close to what we want to have. But it's not exactly what we have, right? So now, okay. We have here Vn and we have Vn minus 1. So if we want to show that this is smaller than this on the left side, the only thing that we still need to show is what we need in order to get a Lyapunov function is then this. Vn of MPC for S1 should be smaller or equal to Vn minus 1 MPC of S1. And if we show that for all S1, right, then we would be ready. Let me just wait for this. Yeah? So that's what we need. If we would have it, I would want to be sure that everyone is on board. Yeah? That if we have it, that then our nut is cracked. Yeah? Why? Because then we know this, right? That implies this. And this, because the C is bigger than alpha 4, implies that it's actually shrinking with alpha 4. Yeah? Because if we would have this, yeah, then this would imply that V MPC n of S1 is really smaller than V MPC n of S0 minus alpha 4 of S0, right? That's from this positive definite assumption. So we just need to choose a positive definite cost. That's like quadratic deviation or something. And if we get this extra condition right, then this whole thing will give us a stability proof. But this extra condition we don't have yet. So let's look at this extra condition. It's basically, what does it say? It says that if you, now let's just look at this. So I look at it from this perspective here, basically here, but I draw it again. Yeah? So I compare two problems, namely one with horizon n and the other with horizon n minus 1. And I compare them, actually here I moved forward the horizon and I shrank it, right? But now after this I need to compare actually this one with a shrunk horizon with the one where I prolong it again, right? And so I will actually plot the picture again. And I will actually not call it S1 anymore because I will want to have it for every S, right? So I will just call it S0 to make things easier to summarize it. Yeah? So S1 will just be replaced to be S0, and I mean, it's just a variable, right? So now I plot here 0, here's n minus 1, here's n. So these are my time steps. Then I have my point where I want to be, okay? And here's my starting point. I call it S0. And yeah, okay. So I will have two optimal trajectories, and maybe I directly, I think for the matter of time, I'd show it for one point, and then we do it. So so this is like a notational thing, but I will add, and this is now a crucial. It's one way to ensure it. I will just say Sn should be equal to 0 in my optimization horizon. That means basically I create this function R so that Sn is 0. We call that zero terminal constraint. Zero terminal constraint. And that's the one I like most because it's extremely easy to implement, so you don't need to think about a Lyapunov function before you construct a Lyapunov function. So you just say that whatever, I mean, it's basically, you could say that your function R is, I mean, you can say R of Sn is equal to Sn and minus Sn, right? That and then this should be smaller than 0, and then obviously Sn must be 0. So just to get the, that's just a trick to make it exactly follow the framework that we have set up above. Later in practice, sometimes people relax that constraint, make it a region around the origin and so on. But at the origin is the easiest, and I think let's think about that first because then my illustration is also easiest to make. So this horizon problem for the shorter horizon, what will it have as a solution? It will have some solution that might actually go, let me just draw it, I mean there will be points in between obviously, right? So that could be my solution, but it should end at 0 because I added this constraint. The good thing is if I add this at 0, there is no terminal cost and I don't have to think about the terminal cost, right? It's always 0 because at 0 my terminal cost is 0 and I will basically not have a terminal cost in this problem. Okay, so now I have this solution, and I know that every single state here is slightly has a positive cost. So what happens if I prolong my horizon by one time step, and then I optimize again? I will get a different solution, right? It could be this solution, for example. So how could we ever know that this is better, right? We want better, right? The longer horizon solution should be better than the shorter horizon solution. But it's a longer horizon, so how can it become better? But we have all tools already at our hands to prove that it's indeed better. So we want to show that this trajectory has a lower cost. That's the optimal one for the long horizon, right? So that's, let's say, S star for n. That's not good. Long, right? And that is S star short for the shorter horizon. It ends here, right? And this one ends there. It's the following is the argument. If you have this trajectory for the short horizon, by constraint, you added this constraint that it should be 0 at time point n minus 1. That's this thing, right? But now the beauty is now, because I impose that as a constraint, so it's now already this design choice, right? So this is like the big one way to make sure that it is.
This is also n, not n.
Okay, sorry. Yes, it's n for this problem above, right? But then there is this n I replace by n minus 1 for the short horizon problem. So it's always at the end of the horizon that it's 0. Yeah. So you're right. But it's in this problem I call it as n, and this n, this n, and this n. You need to insert them in that problem, and then this actually means that Sn minus 1 is 0. You're right. Yeah, thank you. That's a very good point. Yeah. So Sn minus 1 is 0 for Vn minus 1. Yeah? So that's what we need to that we impose there. So actually, and then maybe this becomes now clearer. So we have imposed this constraint here that it should be 0. But this constraint, when we prolong the horizon, will not be present anymore. This constraint will be dropped, right? Instead, we will have the constraint here now. And we have this extra term here. So that's what creates all the difficulty, that we prolong our horizon. And how does that actually work out? The beautiful argument, do you now see it after I've clarified that point? Maybe not the Syscop members, but someone else? Okay, I do it in my words then. So you have a trajectory from the short horizon, right? You can prolong it by one extra variable. You just add this extra Sn equals 0 and the control being 0 here. This way you prolong your short horizon solution to a long horizon solution, which is feasible because you can stay in 0 at 0 cost. It's not only feasible, it has the same cost because you can stay there at 0 cost. This short horizon plus extension has the same cost as the short horizon optimal cost to go, right? But the optimal cost to go for the long horizon problem is the optimal cost to go. So it must be better than any other solution. So it can only be, this cost can only be, because it's optimal, it can only be lower than that cost because it's optimized. Because one feasible solution is this thing, right? So if I maybe write this in, I think I make it explicit by cleaning, did we take a picture for both? No, the one at the top we have already the picture, I think. Or maybe just for safety. We do.
Policy is at least as good as any other one. So
Exactly.
it will be not strictly better.
No, it can be as good as the same. It doesn't need to be strictly better. Okay, I think I will now delete the lower blackboard and I change them. And I think I will make a mini connection to dynamic programming. I mean, this is all based on dynamic programming ideas, right? But at the moment, I'm just having one possible stability criterion, and I want to characterize, so to say, all of them in a minute. So yes, maybe I first listen to the. No, I first explain maybe what I still wanted to explain. Yeah. So I compare two solutions. Two solutions, two feasible points. For horizon n, right? And 1 is actually the trajectory that consists of S0, S1, A0, S1, A1, up to A n minus 2, S n minus 1, right? That was my trajectory, but this one was actually already 0. And then I append 0 and 0. Yeah. So this was this, let's say this, I put a star here. And these are the solutions to the problem Vn minus 1, MPC, at S0. That's given by the minimizer of our sum up to n minus 2 of our extended cost, Si ai starting at 0 and then subject to Si plus 1 equals f of Si and ai, and I goes from 0 to n minus 2, right? So this would be the horizon problem with n minus 1. And and I wanted to add, and I added Sn minus 1 equals 0 as a constraint. Yeah? So that's what I do in the zero terminal constraint. So if I have this, then this is obviously 0, right? And I know that this, the cost of this, the cost, which is actually the cost, I didn't define it, right? Because this is the optimal cost, so I don't want to misuse it. But the cost of that trajectory is actually equal to this Vn minus 1 MPC at S0, right? But it's a feasible point for horizon n, not for n minus 1, but it has the same cost as this. Yeah? And then the other point is now the optimizer of the new problem. Yeah? So that's so x star solves, this is x star, right? Yeah, solves n minus 1, yeah, problem. I take up another chalk. And now I create another solution, which, I mean, it's just to make it absolutely explicit. X star star solves the n problem, the problem of horizon n. And this problem of horizon n is then the one that we had shown before, but it's this one. So everything here, but then it's going from 0 to n minus 1. And here we have the constraint Sn equals 0. Yeah? So you see these two problems are very related. But now we see obviously that this x star is the solution to that thing. It has some 2 stars, right? So it has some values S star star 0 up to S star star n, right? So which is, by the way, this last thing is of course 0, and this first thing is also equal. But I don't. But then the point is that this cost must be smaller because it's optimizing that whole point. And that is smaller, the cost of this whole thing is smaller than this. Okay, so that's actually, in a bit more words, what I've said before. In the previous blackboard, I had already expressed that. But here it's like made a bit more explicit. So I have one solution that I call x star, which is feasible but not optimal. And then x star star is really the optimal solution, and that is better. And because it's better, I have this descent property, and because I have this descent property, I'm happy and everything is good. But now comes the point that I wanted to somehow make a connection to dynamic programming. So if you look at this thing at the beginning, the only thing that we need is that this n function must be better than the n minus 1 function. Yeah? So if you now think back of dynamic programming, Yeah. It turns out, you remember there's this monotonicity of dynamic programming, and V is actually, it's the dynamic programming cost to go. Yeah? And you recall, and now in our dynamic programming language, we had this operator T. And actually what this means, this whole thing means, nothing else than that if you apply T to Vn minus 1, because that's prolonging the horizon means one step longer horizon, right? So T of V MPC n minus 1 should be smaller than V MPC n minus 1. That's actually, recall the language of the DP. So that's the language of DP, where this is now the dynamic programming operator. And if you think of this language of DP, you could also say, hey, didn't we remember something about monotonicity? Yeah, there was something like monotonicity. And how was it like? How was it? So we just need to get something that is monotonous, and then we get it's completely monotonous. And this is actually now the key. So what you can actually show, by the way, I mean, I can apply T now on both sides, right? It wouldn't change the picture, right? So what would be if I just say the following? So T of V0 MPC, if I just say this, could I just start requiring this thing? What is V0 of MPC? That's the problem for no horizon at all. Yeah? So V0 MPC is the same as E bar. E bar being the extended value formulation of the terminal cost. For the zero terminal constraint, my E bar is just 0 and infinity. S, and that would be E bar for my zero terminal constraint. It's just 0 at 0 and infinity everywhere else, because only 0 is feasible. So, I obviously have this property, because I can stay in 0, that if I apply dynamic programming and I go one step backwards, then I have more states from which I can go to 0. At 0 I can still stay, and then if I do one step backwards of dynamic programming, then I get actually V1, right? So this is, by the way, this is equal to V1. Yeah, I should say. Maybe my whole thing, I should just first say that Vk plus 1 MPC is equal to T Vk, right? That's by definition, so to say, right? Prolonging the horizon just means I have more dynamic programming. So now, if I apply the dynamic programming operator to that, then after one time step, I might get something, maybe, and then it goes to infinity maybe, but I have some states from which I can reach 0, and these states have non-infinity cost. And at 0, I will still have 0 cost. So you see immediately the zero terminal constraint has the property that it somehow relaxes this very tough terminal cost. But some other terminal costs might also have the same property, and that's why nearly all MPC stability proofs that are, so to say, based on terminal costs and terminal constraints, they all design, so to say, this E bar, the extended value extension, which is basically a mix of a constraint, which is making what is infinity and what's not, and a cost in the feasible part. So that's why I think of E bar here. If you just have to design an E bar that satisfies this thing. Because when you satisfy this, and you apply dynamic programming on both sides, yeah, then it will imply that, applying t again and again and again on both sides, right? Because of monotonicity, it will actually, this implies that, right? Because of this definition. So when I apply it once again, then it implies actually that the cost V1 is loosening. So basically, if I start with such a restrictive thing here, and then after one time step, making my horizon longer makes it a bit more relaxed. Making it even longer will make it even more relaxed, right? And then whenever I add another step in length, I can make my solutions only better, so to say. Based on exactly the argument that we had pictorially there, but here it's more like from dynamic programming, right, from monotonicity. So if you start with the terminal cost that has this property, then you get the condition that we needed by the monotonicity of dynamic programming. And so the zero terminal cost constraint is just one way to this is implied by a zero terminal constraint or other combinations of E and R. Yeah? So basically the terminal cost and the terminal constraint, you need to make sure that they, so to say, have this property. And if they have that, then the rest is implied. And some other ideas maybe I can tell you already. One, which would be maybe connecting to what we did. Imagine you have a linear system where you have a region around the origin where you're unconstrained. And you have a quadratic penalty. Then you know that in the region around the origin, the LQR law will perfectly stabilize you, right? So what you could do is you could just say, I make sure by a constraint that I will end in the region where my LQR law is applicable. And actually I impose this constraint so that I take this LQR P matrix, which is the LQR optimal cost to go. So I have an ellipsoidal constraint at the very end of my MPC horizon. And then as the cost, I take the LQR cost. And with that, I will also be able to show this whole thing. So, of course, it's very restricted. I need to have a linear system, and I need to pre-compute the LQR controller. But there I can impose this condition. And then the argument, if you want to do the argument like pictorially, like we do here at the top, it wouldn't be like I prolong my trajectory staying at zero, I can stay in zero. No. There you would, so to say, not just append 0 and 0, but you would append the LQR control here, which you know is feasible, and then the resulting state after one step of the LQR control. And then because LQR was derived by dynamic programming, and if you're in the unconstrained region, you're fine, then the LQR control will allow you to keep in this region, and then you also have this property satisfied. Yeah? So let's say the other example that I said would be something like you say, hey, S transpose P S smaller than some factor, maybe some delta, whatever, right? And then, so this is your constraint for R. Maybe I should directly write it like that. So how would I do it? I would just say minus delta, and then this whole thing should be smaller than 0. Yeah? This could be my constraint at the end. This is the function R. And then this is equals of R of S. Yeah, that could be my R of S. And then this delta must be chosen small enough. And then I have my function E of S is given by just S transpose P S. And that is now a way to design from an unconstrained linear quadratic regulator. I could, so to say, design it into a constrained MPC controller with addition of constraints, right? So these path constraints would the main benefit. And this way I can basically construct for a linear system with constraints, stabilizing controller with guarantees, also beautiful because it's stable and because it's convex. I can show that I can solve these problems and so on. So I can actually design a stabilizing controller for a constraint system under the assumption that the origin is controllable. That's all I need, right? The origin must be controllable, and then I just add my penalty my quadratic penalty, I solve my Riccati equation, I get my LQR, and with this LQR I have a cost matrix, and I make the region small enough so that I know that my LQR gain in this ellipsoidal region does not saturate any of the constraints. And if I have that property, then I know that my LQR feedback is a feasible point also for the prolonged problem. So I just need that this point is always feasible with respect to my control constraints. So in that sense, it would be nice to do it in more detail, but that's like one of the highlights, I would say, that because you can really have a constructive rule to design an MPC law that is stable. But if you think of it, it's practically not so different from imposing a zero terminal constraint, because this, you would have to choose this delta possibly relatively small in order to be sure that your constraints are not saturated. And then we could also set delta to a very small value, and then you're basically back to the zero terminal constraint, right? So the philosophy is always the same. You need to impose that at the end of the horizon you want to be pretty close or exactly at the origin, and then you can prove asymptotic stability and Lyapunov stability of your closed loop system. Okay, I think I didn't answer the question yet, right?
No, but this was basically a discussion about there was a whole discussion in the chat.
Okay, in the meantime there was a whole discussion in the chat, I learned,
so,
right? Yeah.
They were discussing whether this isn't a strong condition that we reach at n steps
yes.
fixed point.
Yes,
but
yes.
As far as I've understood now, you can...
Relax. So the question is, it's a very tough assumption, you could say, to reach after n steps already the origin, right? And this is the reason why people want to relax it, and people worked a lot on how to relax it. Yeah. Let me just say, if your state space has dimension 10, yeah, and your control is only one single control, yeah, then by a simple argument, after 5 steps of your control, you can reach just a 5-dimensional space. Yeah? So you can never reach the 10-dimensional constraint at the end by a simple. Yeah? So if you have a 10-dimensional state space and you have one control per time step, you need at least 10 time steps on your horizon in order to make this a well-posed problem. So you should choose, roughly speaking, the horizon length a bit longer, yeah, typically a bit longer than this. The state dimension divided by the control dimension, right? That's, so to say, a first rule of thumb. Yeah? Which is for smaller dimensions not difficult to achieve, but for high dimensional state spaces it gets a problem, obviously. And in particular, if you have, let's say, distributed parameter systems, which like heat equations or such things, they could be still nice and linear, and then you could still maybe be able to solve Lyapunov equations, or actually Riccati equations, sorry. And if you have a Riccati equation solved, then you can maybe relax that to a region. And that's, this thing is, so to say, already nicer because it's a region around the origin. It's an ellipsoidal region, which, so to say, leverages the Lyapunov property of the LQR matrix. In a small region, that is a Lyapunov function, and you just use the MPC to create a controller that is valid in a larger region, including the region where you might have control saturations, where the LQR, you cannot prove stability of your LQR for that bigger region. It is not stable. It could actually even be unstable there. But just clipping, for example, your controls, your actions, while the MPC is stable if you impose this little condition here. So it's a mix of design and proof and so on. But I hope you got the ideas and the connection to dynamic programming. I was very happy when I understood this for the first time, because you can have long papers, right, that try to express this and prove from this that one. Yeah, but dynamic programming does it very quickly. Yeah, so we remember it from dynamic programming. There is monotonicity, and with the definition that prolonging the horizon is just an application of dynamic programming, you can immediately apply T n times, and then you apply what you want to show. From a terminal cost property, you imply the Lyapunov property of your cost function. And maybe I should say one thing. There are people that focus on just proving this, independent of that. And in fact, you can prove also for some MPC, I mean, roughly speaking, if you make your horizon long enough, yeah, independent of what you do here, this property will hold. But the question is, how long should it be? Yeah? So the intuition is that the importance of the end term is somehow vanishing when your horizon is long enough, and so at some point you get to this property even without having that. So this is just an implication, a way to always guarantee it for whatever horizon. But if you are, so to say, happy to use other techniques, one could try to directly prove that one, and that's another stream of research for people, in particular when they're concerned with MPC without terminal cost. Yeah, that's like if you Google for MPC without terminal cost, then you will find interesting papers that directly prove this property without building on that. And that is maybe a bit more close to practical implementations of MPC, because very often, like you've seen in our Corona example yesterday, you just don't impose anything at the end. You just say, let's have zero cost at the end. Yeah? And that's very often the default assumption. Mm-hmm. Thank you very much.